Hey there, I'm Alex. In this recitation, we're going to be covering block processing. So, what are blocks? I think it's better to start with our general way we look at neural networks. When we think of neural networks, we usually think of them in like a layered approach, and we think of how the layers are structured. And often, you won't even really be thinking of things in blocks at all with really small neural networks, because in one or two layers, you might actually just be done. That might be the network. But when you start getting into larger neural networks or reading white papers, you'll start to see that different networks can have hundreds of layers, and that oftentimes they'll just be a repeating pattern in the structure. For example, convolution of different size, another convolution, and then you just have an activation. And this is generally what we would call a block. The idea of compartmentalizing a network that's quite large into repeating structures and patterns, and this is pretty standard. For example, ResNet is a really, really common example of this. It's entirely consisting of just blocks. So right here below is a good example of a really simple block. So formally, a block has to be a class that has a forward method and a backward method, and the forward method has to transform each input into an output. But you might notice over here, the forward method is quite straightforward. It just self block X. And there isn't a backwards because AutoGrad handles it for us. So yeah, this is a really, really simple one that's just a conv2D, batch norm, and then ReLU. That's kind of the thing about blocks. It's more of a conceptual way to organize things to make it easier to understand. So whenever you're reading a paper about ResNet or SE ResNet or ConvNext, you can essentially conceptualize it in terms of what are the shapes of the blocks and how are they designed, rather than the entire thing, and that's the whole appeal of it. Not to mention the modularity makes it much easier to work with. So earlier I'd mentioned that you usually want to talk about blocks whenever you're dealing with networks that are much larger. Generally, it's helpful in general with convolutional neural networks, but something like ResNet is often over 100 layers in size, which makes sense. So what are the obvious problems with that? Well, most obviously is the vanishing gradient problem. So you end up thinking that it would make sense that if you're trying to make a network that can approximate some complicated function further and further and further and be closer and more accurate as you go, that you're eventually going to want to have a network that's deeper and deeper and deeper and deeper. Well, not quite, not in all situations. Sometimes you are trying to approximate some function with a network, and indeed you find some paradoxical relationship that the deeper you go, it actually seems to get worse after a certain point. So there were some papers back in the day that found that you don't want a network to be too deep, and you don't want it to be too shallow. There's a kind of a sweet spot. When you keep on adding additional layers and making the network deeper, it improves till a certain point when it starts to go backwards. And one of the inherent problems with a block-based approach is that your networks are quite deep usually, because the whole approach for CNNs like this is that you might have many blocks and considerably more blocks. You can increase thickness, but that may not necessarily do it for you for certain functions. A weird paradoxical example of an easy function that you'd think might be able to do quite well and be easily able to be approximated with just about most neural networks is an identity function. Well, if your network's too deep, it might not be able to approximate it. So this is ultimately why we have residual connections. So residual blocks use residual connections, and they're a type of shortcut that skips one or more layers during forward and backward passes. The whole idea of this is you want to add the original input x to the output of some f of x at some point of the block, making the output f of x plus x. The whole idea is, instead of suffering from the whole degradation problem earlier in having vanishing gradient issues, if you do this, you preserve additional data as you're going. So you don't really suffer from vanishing exploding gradient problems as much, since x is preserved throughout the entire network. We can see a diagram of this over here with a deeper residual function, an ImageNet. Notice how right over here we have that we pass right through, and we append x right where the ReLU is. There are also some other advantages, such as it may converge faster and training speeds better, and generally that you can have a much deeper neural network without suffering from nearly all the problems that you'd be having if it was otherwise. All right, so let's also cover depthwise and pointwise convolutions. Depthwise convolutions apply a single convolutional filter per input channel. Pointwise convolutions are 1-cross-1 convolutions that combine the depthwise output channels. So what does this mean? With depthwise convolution, we apply a single filter per input channel, which is drastically more parameter efficient. And with pointwise convolution, we reduce the filter size to 1 times 1, which is significantly faster. If we look down over here, we have a standard convolution. So this is going to be 64 times 256 times 3 parameters, which is going to come out to about 1.5 million almost. But if we look at the depthwise convolution, we get 64 times 3 since we don't need to do the multiplication for 256, and it just becomes drastically less parameters at 276, and then the same thing goes on with pointwise. Since it's only 1 times 1, we're only concerned with 64 and 256, giving us a lot less. These are usually combined together, so you will end up seeing something like ConvNext, for example, or MobileNet that use these quite a considerable amount in their design. Coming down over here, we can see that here's an implementation of pointwise and depthwise. In Torch, we can see that if you're trying to get depthwise working, you just need to have groups be equal to in channels. And when you want to get pointwise working, you just need to set the kernel size to 1. And yeah, over here, forward is depthwise, pointwise. These are used pretty excessively in a lot of different and really famous convolutional neural networks like Exception and MobileNet and ConvNext. And you can use them yourself because they're very, very efficient in parameters, which might actually end up being quite useful, and perhaps it could help you out with homework 2 or homework 3 even, especially in homework 2 where parameters are possibly going to be quite tight.